Um, so there's one question here about a movie from a movie buff, I think, who watched Christopher Nolan's film Interstellar, and they'd like to know whether it has any veracity with about real black holes.
There was a lot of physics put into that movie, Interstellar. The Nobel Prize winning physicist Kip Thorne was a consultant on that. And many things about, when the people go close to the black hole and stay what seems to be a short time for them, and they come back and many years have elapsed on the spacecraft. That's all true. Time slows down when you're near a black hole, and you'll age a lot more slowly than people far away. A lot of pictures of what it looks like, stars with the light bending as you approach a black hole, those were all accurately portrayed. In fact, they solved Einstein's equation to get some of those shots for Interstellar.
Kip told me the following thing. He said, of course, it's very expensive computationally to do a lot of ray tracing, right, around this. But they did have to do it to make the images in the movie, and that was the best job on ray tracing in the film. Was much better than any calculation that was done by the physicists. They had more money than the physicists.
So it's a question for Jim about your talk. So you showed a picture of the universe, which was smooth space-time, and they were asking how that could be consistent with a Big Bang, or whether it's consistent with a Big Bang.
All those galaxies are far away from the Big Bang. So it's now, right, that it's more or less homogeneous and isotropic, not at the Big Bang. That's correct. It's not homogeneous and isotropic for all time, only late. Yes?
Yeah, another question for Jim. So you mentioned that there were no observers in the early universe. This is perhaps this is a rabbit hole, but they were asking what counts as an observer.
I just meant an ordinary human observer, right? Or even a mouse. The temperature, after all, was extraordinarily high. There would be no life at all in the very early universe. So we don't have to get into a definition of what an observer, because it's not important for decoherent histories quantum mechanics. That was the entire thing. We have a better version of quantum mechanics that doesn't rely on observers and measurements. Observers and measurements can be described, of course, in realistic terms using that quantum mechanics, but the theory is not dependent on them.